Hi, welcome to CSE351 Introduction to Data Science, and this chapter is Building Models. Okay, so let's look at the data science analysis pipeline one more time to get some idea about the different tasks involved, because this model building is a very integral part of data science pipeline. So let's start like what do we do in data science. So we start with asking a question. The question should be interesting for our project that we want to do. So that involves finding out like what is the goal of the project that we are undertaking. We want to find the answer to a problem, and then that problem should be well stated. There should be an interesting question for that problem to be pursued. Then when you have a question, then the question answer to the question should be obtained from data. We need to get the data for that problem. Well, we'll find some data, and if we are lucky, then yeah, good, we'll either get it directly from somebody, or we will have to scrape the data. So there are a lot of things that we might have to do to get the data. After the data, once we have it, we will do the exploratory data analysis that will involve some visualization, some plotting, and on the basis of that we'll have some understanding of the data. Then comes the most important part, which we will look at in today's lecture, that is about building a model. So model building means that from whatever we have gathered, whatever we understand from the data, after training it, after visualizing it, we want to say something about future. We want to predict something. We want to say something about unseen data. So whatever data is available to us, we will learn from that data and we'll do some forecasting or prediction for the future unseen data. So that's the purpose of modeling. We have to learn something from the data. Okay, so that's something we will look into in this lecture. And the last stage in the data science pipeline is about communicating our findings to the other people who are interested in knowing about our result. So if we are working in a typical industrial setup where we are the data science team, then probably we will have to report our findings to the people in the management in a form that they can understand. So that will involve some visualization approach. But let's confine to the data modeling for this lecture. So if you're looking for the definition of what data modeling is, then I find this interesting one. So it's a process of encapsulating information into a tool which can make forecasting or the predictions. And here we'll have to find out, we'll have to build a model, and then we need to evaluate how good the model is, how well is the model fitting on the data that we have. Okay, so let's see what we have here. Now when you need to pick a model, you will have different choices. So given a data set, because of say we are given some data set and we want to make some prediction, if some data is available about the stock prices today, and someone is saying that what would be the stock price say after 1 month from now. So there we need to think about it, right? Okay, the data is given to us. Now what are the possible models which will be good for this task? So there are certain philosophies involved in picking the best model. So let's look at that. Like, what are the challenges involved in picking one model from the set of available models? So there are these three important philosophies which we will look at. Occam's razor is a very interesting and popular philosophy in picking the model. Then we have the statistical, I won't say statistical, but this is the bias and variance trade-off philosophy that we have. It relates with the statistics. Statisticians, they talk about it. Bias and variance trade-off, we'll look at that. And then the third point is from a person who's very well known in data modeling and statistics, Nat Silver. So he has written a book titled The Signal and the Noise. So we will look at different principles that he follows in doing modeling. So let's start with the simplest, the first one, which is Occam's razor. What does it say? So the Occam's razor is a very interesting philosophy that says that if you are given two models, and you have to pick one of the model from the two, and these two models are very similar in terms of the performance, then you better pick the simpler model. Okay, so this philosophy principle states that the simplest explanation is the best. Okay, so why so? Well, it relates with other concepts in machine learning as well, like overfitting and underfitting. I'll explain that to you when we discuss the bias and variance. But you need to understand this philosophy that whenever you have an option to pick from two models which are kind of doing the same, performing to the same level in terms of the performance, then we should give the priority to the model which is simpler one. Okay, so now the question is, okay, it's easily said that simpler one. What would be a simpler model when we are thinking of modeling? So for that thing, let me use my pen to give you an example. Suppose that you have two models, model M1 and model M2. Let's not go into the details of what M1 is, what M2 is, and let's think that the input data that I have, call that X, has X would be a matrix, so it has a number of rows and columns. Let's only think about the columns, which means how many attributes do we have for X. Assume that we have attributes like, okay, let me make it a table, that will look better. So why I'm making a table? Because then it will be easier to visualize, like how does the data look like. Now you will have x1, x2, these are the sample data. Assume that I have x and data points, and then for each data sample that I have, assume that I have these features like f1, f2, fn, fm, right? M should be different than m. So there are m features. You can also think of features as attributes if you want to understand this data from database point of view. Features or attributes. So our data has m features or m attributes. So each data sample that you have in our data set will have m attributes or m features in there, and there are total n samples. N samples means we have n data points. Now let's think about M1 and M2. You have designed the model M1 in such a way that it uses 10 features. Alright, it is based on 10 features. Somehow you found out that for whatever prediction you have to do, you're using 10 features out of M, and I can make M, maybe let's say M is equal to 30. There are 30 features in our data, and the M1 that you created, the model that you created, is using 10 features of this data set, whereas the M2 that you have is based on only 3 features. Alright, so in this context, I mean, one of the way in which we can judge whether M1 is simple or M2 is simple, I will say M2 is simple. Why? Because M2 is using less number of features. Alright, so one of the way in which you can judge the models as simpler is look at the number of features which are being used in modeling. Alright, so features are also called as parameters. So the next point that we have is about the same thing. With respect to modeling, we might think of minimizing the number of parameters in a model, right? So since M2 has less number of parameters, which is 3 compared to M1, so we will prefer M2 over M1, provided M2 and M1 are giving the same performance level. Alright, so if I say that the accuracy of M1 is 95% and M2 is also like 94.67%, right? So these two are pretty close, but M1 is more complex compared to M2. So according to Occam's razor, I should prefer M2 because M2 is simpler. Okay, so this is so important and so popular in machine learning, and this concept has given very good results, and because of which even some algorithms like lasso and ridge regression, these are some more complicated or more advanced linear regression algorithms that are present in machine learning. These algorithms have this thing inbuilt which will penalize if you have more features or more parameters, right? So machine learning methods like lasso and ridge regression, they have a penalty function. Okay, so this penalty function will enforce that your model is not learning too many features, right? So these algorithms will inherently have this feature which will encourage picking the simpler model. Simpler model means less number of features. All right, so features or parameters or attributes, they mean the same thing, which means the columns in the data set that you have. But there's one point which is always advisable. This is to follow some sniff test. Sniff test means just look at the result and make sure that whatever you're getting is making sense. All right, don't trust anything blindly. Right, look at your results that you're getting and look at the model that you have and then act accordingly. All right. So now the other classical approach that is kind of considered while picking the model is bias-variance trade-off. So now what is this bias and what is variance? Let's try to understand these one by one. So I will start with bias. What is a bias, right? So bias is related with our preconceived thought about a model, right? So what can happen is that we might be somehow tempted to use a certain kind of a model for our data, right? And that model may not be good for the data that we are working on, right? So this bias is something that we had in our mind or in our thought process before even looking at the data, and because of which you will have the error. Okay, so the bias error would come because of the model that your user has picked with some assumptions, and those assumptions were incorrect. All right, so is an error from erroneous assumption about the model. All right, so uh, as an example, we thought that probably the data that we have is a linear, and so it is linearly separable, and we should try a linear model. But it turned out that it's not linear at all, right? The assumption that we were making that a linear model will work for this data set might be wrong altogether. Okay, so the bias is something which results from our assumption about the model. Alright, so if you are having an assumption about the model which is totally wrong, then you might get an error which will be called the bias. Alright, so again, as an example, if you assume that you'll be using linear model for certain data and which is not linear, then you will have the errors, and this error will be called bias. Now bias results in something called as underfitting. Okay, so underfitting is a problem where when you're training your model on the training data set, then it performs poorly. Alright, underfitting happens when your model doesn't fit well in the training data. So if your model is not doing well in training data, definitely it will do really bad in the test data as well. Okay, so the bias error relates with erroneous assumption, and which often results in underfitting the data. Now what is the variance? Variance is just kind of opposite to bias. Now in case of variance, what happens is that when you train your model too much, to the extent that the model has even learned some noise in your data set, then that will result in variance. So the result of that would be that if you try this model on a test data, then the model will do horribly in the test data, but the model will do exceptionally well in the training data. So that happens because of overtraining. When you train your model so much on the training data that it learns even the noise that you have in your training data, then it is bound to perform horribly on an unseen data set, right? Which is called overfitting. Overfitting means training your model so much on the training data that it does poorly on the test data. Why is that happening? Because you're overfitting, and this fact is called this kind of error is called the variance. So what is it? It is the error from the sensitivity to small fluctuations in the training data, and this small fluctuation could be because of some noise that you have in the data. Alright, so as an example, as has been beautifully given in the textbook, assume that we have again this, we can go back to the previous slide. Assume that we have this data set which has m is equal to 30 features in it, and what happened, you were too much obsessed with the training error. You wanted to reduce the training error, so you trained your model so much to the extent that the model learned all the 30 features. All right, and of these 30 features, there were only some features who were correlating with the target. Okay, so let me also add one more feature right here, which is the target. Okay, so target is something you want to predict. So you trained your model so much that it learned all the 30 features, and in reality all these 30 features were not strongly correlated to your target. Alright, because of which, if you are trying to evaluate the performance of this model on the test data, then it will do poorly. Okay, so this kind of error that we are getting is called variance. So now the point is, what is better? Should we prefer a model with the low bias or a low variance, right? So the point is that we should pick a model which is giving us a good performance in terms of bias as well as in terms of variance. So we don't want underfitting, we don't want overfitting, we want some compromising solution. We want a model that is doing well in terms of bias as well as variance. So we should not have any assumption. We should not make any erroneous assumption, because if we do that, we'll have the error because of bias. And if we overtrain our model, then you'll have the error because of the variance. Okay, so now I will look into these kind of models which are called first principle model and data driven model. We'll look at the model taxonomy, like how do we define different kind of models. Then I'll tell you about these two kinds of models, first principle model and data driven model. Let me give you some idea about what first principle models are. Now, the models which are based on some principles, and these principles could be from the laws of physics, or could be from some systems which are well defined, right? So if the data that we are getting is from some physical principles like the laws of motions and all, where we know we know something about the phenomena that is generating the data, right? So that kind of model where we know about the system that is generating the data, they are called first principle models. All right, and there are some other models where we don't know anything about, or we don't know much about the system that is generating the data. So it is not like the laws of motions and something like that. In those cases, the only source in which we can learn is the data driven approach. We learn from the data itself. We have no insight in the process that is generating the data. So of those models which are first principle based, we have the chances of bias there. So these methods, they suffer from bias, whereas the data driven models that we have, they suffer from the problem of overfitting, and overfitting relates with the variance. All right, so yeah, that's the takeaway lesson for you. The first principle models, which are based on some physical phenomena, or some system that we pretty well know, that we understand really well, those are susceptible to the errors because of bias, because we can make some assumption about those, that this is how the data is being generated, and that assumption may go wrong, and which will result in the error because of bias. Whereas in the data driven model, we won't have anything, we won't have any insight into the system or the process that is generating the data, and the only source of learning for those models would be the data, right? And in an effort to reduce the training error, what we end up doing is we may end up training our model too much, and you train too much, then that results in overfitting, and which is called a variance error. And if you're overfitting your data, then the performance of your model would be very bad on tested data. Okay, so this is the philosophy about bias and variance trade-offs. Look for a model which is giving you the best value of bias variance errors. And these are, if you improve bias, your variance will go down. If you improve on variance, your bias will go down, because bias corresponds to underfitting, variance corresponds to overfitting. All right, now to this principle of Nat Silver. So as I was telling you, Nat Silver is one of the most successful modeler or data scientist, you can say. He has been very successful in modeling. So initially he was working as a consultant, and then he moved into the modeling of baseball games. He used to do predictions for baseball games, and then he moved on to the forecasting of the election results. So he started forecasting like who's gonna win. So in the year 2008 and year 2012, his predictions were great, and because of which he got a lot of popularity, and he was able to do okay in the year 2016 as well. So what we need to do is we should look at his approach, like what was the reason behind his success. So in his book, which I mentioned in the previous slide, let's go back. That's the signal and noise, right? So there he has mentioned some philosophies. So what are those philosophies? So he's saying that when you have to build a model, then in model building we should think probabilistically. What does that mean? I will explain to you in probably the next slide. Then your model should be such that it should be dynamic, right? So he's calling it that your model should be live model. It should not be dead. So what is that? We will look into that in the next slides. And similarly, when you're doing a model building, then you should look for consensus. Okay, so what is a consensus approach? That's also something we will discuss in detail. And you should use Bayesian reasoning. So these are few things that he always follows whenever he starts doing the modeling. So let's see, what do we mean by thinking probabilistically. So Nat Silver says that it is possible to design a model that would say, the result, like what's the outcome. So let me give you an example, right? Let's think about a scenario where we are designing a classifier, and the classifier is for the data which is about the patients, and the patient data is about cancer, right? So if a patient's data is given to you, you will have to say whether the person has cancer uh, or not. So yes means a positive result, which means the person has cancer. No means the person doesn't have a cancer. No means a negative result. So what Nat Silver says is that we should attempt to always answer on the basis of probability, right? So we should not say, our model should not give the result that this data x1, yes, that means that this guy has cancer, or x2, when you say f of x1, which is your model, then the model will say yes or no. Yes means this guy has cancer, and no means this guy does not have a cancer, right? So yes and no you can have as 1 or 0 when you implement that. Let me put 1 and 0. It's an implementation based issue, but let's try to understand the philosophy. Now this is something NatSolver is saying is not a good idea, right? That's something we should avoid doing. What we should instead do is we should give some probability, right? So what is the probability? So this we should build our model in such a way that the model should say that 70% chance that it is cancer, right? So output should be 70% chance of cancer. So we don't want yes and no, okay? And 30% chance that it is healthy. Alright, so we should be making probabilistic model, right? So it's very interestingly discussed in the textbook, but the message is that we should think in terms of probabilistic approach. The output should be probabilistic rather than deterministic, okay? Now that's what it is, right? We should think of generating the probability distribution over all the possible events rather than just picking one event and saying okay, that's the result. No deterministic thing. Let's think probabilistically. Now alright, so there's one more interesting thing that we have here, which says that the good models do better than baseline models, but you could get rich predicting. Alright, so this is about the models, like how good your model was, right? So this point is saying that if your model is doing slightly better in certain important cases, then it will be considered a good model. So here we are discussing about the stock market. So stock markets are so uncertain, so complex that even if your model is coming up with the probability of 0.55 and says that the stock of Microsoft will go up or down with the probability of 0.55, so even that is a valuable result, because if you consider just a baseline model which says that it can go up and down and that will happen with 50% probability, then even 55% is a lot better than 50% for a very complex system like stock prediction. Okay, so this point you might find unrelated with the previous two, but in fact it is related and it is giving you some insight about the result, right? So we are reporting the result, probabilistically, reporting result probabilistically. You're not saying that it will go up or go down. You are saying that it will go up by 55%. Alright, which is more than 50%, and in this scenario it might be a good prediction. Seems like it is a good prediction because so complex is the stock system behavior. Alright, so let's move on. Now there are a few things we should keep in mind when we are dealing with probabilities. We should make sure that when we are reporting the result in probability using our model, then the probabilities that we generate for classifying different classes, they all should add up to 1, right? That's the rule of the probability. So make sure that if you are making prediction for different classes, then these probabilities should add up to 1. That is about the rules of the probabilities. We should not in any way go against these rules. These properties must be satisfied. The probability should not be negative, and there are some rare events, and the rare events will have very low probability, but we should not let that rare event have the probability of 0. That is bad. Okay, so there's another interesting point about being probabilistic when we are building the model, and that has to do with humility, right? So we are not saying anything in arrogance like it is cancer or it is healthy, right? What we are saying, we are stating our result in terms of probability, and that makes a lot of sense because the prediction of any event in real life is a complex process, and the world around us is very uncertain, right? So it makes a lot of sense to be probabilistic in terms of our results. Okay, and in the modeling, there's another interesting thing. In the modeling, we should accept honestly what we know and what we do not know. Alright, so the model must be honest in what it is doing. And I believe being honest is something which we can reflect using the probabilities as well. So if we are saying that the probability of somebody winning an election is 30%, so that means it is showing that our confidence is low, right? So which kind of reflects that we are honest. Okay, so the models, they should have honest in there. The model should say what it can predict and what it cannot. Now there's this very interesting function which is very important, and you'll find the application of this function in machine learning a lot, and this is sigmoid function, which is also called logistic function. Now the question is, why is this function so important in present discussion that we are doing? So if you remember, the very first suggestion that Nat Silver has given is that we should be probabilistic. And he's saying that rather than giving a score in the range of minus infinity to infinity, let's try to map that score in terms of probability. So if there is some score that can range from, okay, let me put that here. We are thinking of very, general case. Let's say that the score that we have, which we are getting from the classifier or our model, right? Classification is one specific case of modeling. Let's think of any general model that we are building. Now that model can give us a range of result from minus infinity to infinity, right? And minus infinity and infinity cannot be a probability value, right? So this is not this doesn't look like probabilistic. This is the true score. I already have true score one more time. This is what we are getting, the result of our model in the range between minus infinity to infinity. Now probabilistically, if you want to convert that into probabilistic term, then it should range from 0 to 1. Alright, so we need some means of converting these values in this huge range to the value in the range from 0 to 1, because probability maximum that you can have is 1, the minimum that you can have is 0, and nothing negative is allowed. So fortunately for us, we have this method which is called Sigmoid method. Alright, that is given right here. Alright, so assuming that this score that you have is T. Alright, this is the T score. Let's call that T. T. Okay, the score that you're getting is T, which is varying from minus infinity to infinity, and that's the score that your model is generating. Then how can we map that to probabilistic score which goes from 0 to 1? So for that we can use this sigmoid function, which is written as 1 divided by 1 plus e to the power minus t. Alright, so now let's plug these extreme values and try to find out like what will happen when our t is minus infinity. So when you put minus infinity here, then that will become positive infinity, right? And now 1 divided by positive infinity, that means 1 divided by infinity is 0. Alright, so this extreme value that you have, minus infinity, so if you say sigmoid of minus infinity, then that is coming out to be 0. We just figured it out, right? So original formulation has 1 over 1 plus e to the power t, but t is minus infinity here, so which will make minus infinity and minus sign cancels out. So this e to the power infinity is infinity, very big number. So 1 divided by infinity is 0. Okay, good. So now let's pick the other extreme, which is sigmoid of infinity. Alright, so for that thing what we will do, let's put that here, 1 over 1 plus e to the power minus t and minus sigma. Alright, we will not change sign here because we are looking at sigma, the positive infinity. So this will result in 1 divided by 1 plus 1 by e to the power sigma, which is infinity, right? 1 divided by infinity, we know it is 0. So the result of that would be 1. Alright, this term will be 0. So the sigmoid of sigma is 1, right? So we are getting this range. Minus infinity is being mapped to 0 and positive infinity is being mapped to 1. Okay, let's look at some intermediate value and try to find out like what will happen. So we will try sigmoid of 0. Alright, so it will be 1 over 1 plus e to the power minus t. A minus of 0 is 0, which is 1 divided by 1 plus 1, which is 1 divided by 2 is equal to 0.5. Okay, so do you see here? Alright, and this is 0. So that's a perfect function for our purpose, right? We can use sigmoid function to map any score which is coming from minus infinity to infinity in this range, which is from this range. Look at this curve here. So the minimum value that this curve is taking is 0 right here, something towards the minus infinity, and the maximum value that it is taking 1 is somewhere towards the positive infinity. Alright, so this is a perfect function for us to map any score in the arbitrary range from minus infinity to infinity to 0 and 1, which we need for probability. And now again the same point that we had in the previous discussion, we should make sure that these probabilities that we are getting, somehow we normalize it such that while we add all these probabilities together, we get the sum as 1. Alright, so you might, if you have multi-class classification problem and you are getting the values like P1, P2 and P6, then what you should be doing, you should normalize all these things by putting it as P1 divided by P1 plus P2 plus till P6, so on and so forth, right? So that when you add these things up, when you add all these probabilities up, you get 1, right? So summing up the probabilities over all events S defines the constant 1 by S to multiply each so that they sum up to 1. So that's the point. Do this translation in the probability and then normalize the probability so that when you add these things up, you get the sum as 1. Right? Just to make sure that we are not doing anything against the rules of probability. Alright, now the other interesting thing that Nat Silver pointed out was about having your model as live model. So now we have this discussion, right? What is a live model? And when you're saying live model, then there should be something which should be called as dead model, right? So let's look at the dead model first, and then if you understand dead model, then understanding the live model would be even easier. So dead model would be something like this, I'm working on some problem, I want to predict something, right? Say I want to predict the flu. Alright, so what parameters I'll get, it is a different question, but let's think that I have some parameters which will determine whether a person has flu or not. So I got that data luckily from some hospital, and I built a model which will say that whether the person has flu or not. The data was good, and I have a model which is telling me about that fact. Now I will call this method a I will call this model a dead model because I got some data and I built the model on that data, and I'm not updating that data any further. Right? So the point is that your model has been built on some data and you are not updating your model. And how can you update the model? Well, you will be updating your model when you're continuously feeding in the data as you get, right? So you're connected with the outside world, and momentarily you're refreshing your training data, right? And when you're refreshing your training data, then by that process your model that you're building would be always in tune with the data set available. Alright, so that's the point. So he's saying that your model should be a live model where you should continuously update your data and you should make your model in sync with the latest data available. Alright, so that's the difference between the live model and the dead model. A model is live if it is continuously updating. Continuously updating predictions. How? By incorporating more information, right? So we should not close the channel. We should not close the input data for our model. We should keep supplying new information as and when we get, so that our model keeps updating, right? And it is in sync with the latest data. All right. So now when you have your model, a live model, which is kind of learning from your data, then a lot of interesting things can happen. So I believe that this guy, Nat Silver, has been so successful mostly for the case that the kind of models that he has been developing were like ones that needs to be like model. Just think about the elections, right? So maybe in the year 2012, I believe in 2012 or 2000, yeah, or 2008 or 2012, what he did was, he started with a model and did some prediction, and just as you come closer and closer to the elections, there are a lot of things that keep happening. So because of his life model, he was continuously feeding the recent developments in his model, and the model was refining, right? And it was live, and it was updating with all the information that he was getting, um, what we should say, real time, right? So I don't know whether we should be calling it real time, but the point is that he was continuously updating his model, right, and continuously feeding in the information that he was getting from the happenings around him. So that might be the reason why he was able to predict the election results so precisely. Okay, so this point that I have here, it relates with the example that I'm giving you. So your model, if that is live, then it is forecasting something, then this forecast should converge to the right answer. Okay, so since you have not closed learning, right? So you're continuously learning, and you are continuously accepting data. So if you are trying to forecast something that will happen in future, then just maybe few days or few hours before that event which is about to happen, your results should converge to the right answer. Okay, so I can give you another example based on that. So how about weather prediction system, right? So if you are a snow lover, right, so you're waiting for snow, and the weather system, or these weather scientists, they will say that 2 weeks from now on Sunday we will have snow, right? So what will happen, actually, that might change, right? So 2 weeks in advance we can say with some percentage that it might snow, but when you are very close to the Sunday, right, when it is predicted for snow, you'll have the best answer, right? So because of this life model, more information is absorbed, and the model improves its prediction. And maybe on Saturday evening you will know for sure that whether it is going to snow on Sunday or not. Why? Because now you'll have more information, right? More precise, more timely information, on the basis of which you can converge on the right answer. Okay, so it may so happen that the conditions totally changed, and what was predicted as 80% of snow is just no snow at all. Okay, so yeah, that's an important thing of life models. Your forecast should ultimately converge to the right answer. But this convergence thing needs the model to be dynamic, to be live, working all the time. Okay, and it's a good idea to have the display of your previous forecast as well, right? Because that will give you a lot of insight about the predictions. Like, maybe you were expecting person A to win the election till say March of 2020, and then it got changed a little bit, and person B is leading by say August 2020, and probably person A wins the election uh, in November 2020, right? So if you have this display, if you're keeping the records of your prediction over the time, then it will give you a lot of power to look into the events, like what caused a person to lead for a certain period of time, and then the other person picking up from the next time, and the winner finally winning at particular specific time. So you can correlate your results with the happenings around us. All right, so displaying the past forecast is also a valuable thing to have, which if you really want to look at, then I'll recommend you to go to the website of Nat Silver, and you'll find very, very interesting results from his modeling. Now, does the model retrain on fresher data? This is something again you need to figure out, like, is that happening or not, right? It should happen. Your model should retrain. You should keep it fresh, and that will happen only when you have this notion of training your training your model over and over again on the newer data. Because if you don't train it, then it's useless, right? So feed your new data and train that again. Keep feeding, keep training, and that way your model would be live, would be more effective compared to the dead model. Alright, so we learned about two philosophies of net server. One was being probabilistic, the other one of having live models. Now, the third point is about looking for consensus. So that's again a very interesting suggestion by Nat Silver, and that suggestion says that we should not always be focused on our model. We should also look at the models around us. We should look at the results which are being produced by other people. Okay, so if we want to stick to the prediction, like who's gonna win the election of 2020, the US election 2020, so your prediction might say that person A is winning, but there might be another source which is saying person B is winning, right? So what you should be doing as a modeler, you should also look at the prediction of the other person who is predicting person B winning. All right, because that will kind of give some scope for consensus, and consensus is very important to have. I will show you a result in the next in the next few slides, which is about some modeling which was done by Google, and it was a very nice system, but they had some problem because of the lack of consensus. So consensus is also very important to have in your modeling. Look at the results that other people have, and by looking at their result and your result, either you'll have the confidence if they are getting the similar results as you are, or it will give you some scope of introspection in your model, trying to figure out like why are you not getting the result that they are getting, right? So you'll have some confidence. So consensus is important. So consensus is something you can also obtain by building something called as your baseline models, right? So what is baseline model? We have a section in today's lecture that discusses what are baseline models, but I can give you some intuition right here about baseline models. So baseline models are some simple model, right? So as an example, if for some reason you are doing some modeling and you think that it's a very complex task, and it's and probably you need a very sophisticated machine learning algorithm for that, and you thought, okay, fine, let me go with the best and I'll use deep learning. Okay, so you picked some deep learning approach for modeling, but the best approach whenever you're doing modeling is to always start with a simple model, right? A simple model which is a reasonable assumption, okay, and might not be very sophisticated, but should give some decent result, right? So what you can do for your modeling also, start with some baseline models, right? So these baseline models could be some existing concepts that people have used a lot, all right? Or maybe this is a very simple algorithm from your understanding of the of the domain. You can start with this base model, and then from this base model, you can a baseline model, you can develop your more sophisticated model, like involving deep learning, and can say something about it, right? And then if you have a baseline model, then you will get some result using baseline model. All right, so now when you are getting results from your more complicated model, like deep learning based model, you can refer back to the results that you are getting from baseline, right? Is the baseline model that you have giving the same result as your more sophisticated model, right? If they are in sync, good. If they are not, then you need to think about it, like why your baseline model is giving result A but your model is giving result B. So consensus is something you can establish using your own baseline model as well. All right, so these are some very interesting suggestions by NetServer. Now, you can also have multiple models. You can for consensus building, and if you're doing some research, right, thinking about publishing some research, then usually you will have to try multiple models, right? So as an example, you're using logistic regression, you are using neural networks, you're using decision trees. So you can try all these different models and look at the results that each models are giving you, and then try to form a consensus. Okay, so this is important. Now, consensus are so important that we have a technique called boosting in machine learning. All right, which does what it does is uses a lot of very a large number of weak classifiers, and using large number of weak classifiers, it does the modeling, right? So in a way, this boosting is also encouraging consensus, and boosting is a very successful approach in machine learning, which involves a kind of consensus. Okay, now this back to this example that I was citing you, like what happened to the Google flu trends, and what was this project about. So Google has an amazing idea or a project where they wanted to predict the flu. Okay, so it was a very interesting project for the reason that um, if someone can predict the possibility of flu, right, a flu outbreak well ahead of time, then a lot can be done um, to take care of it, right? So what Google thought of doing was to look at the search, the query that the user is doing on Google, and on the basis of the keywords in the query, try to predict whether there is a flu, or whether we have chance of flu or not. Okay, and what could be the other source? We can have other organizations also, like CDC, doing the same kind of thing, but CDC does that in a different way, right? So what CDC will be doing, CDC will have its own source of data. CDC will reach out to the local hospitals, will get the data from local hospitals, and then on the basis of the data that the CDC is getting from the local hospitals, CDC will make some prediction about flu. But that will take some time. Reaching out to different hospitals, getting the data and its analysis will take some time. But Google people were smart, right? What they have to do is similarly look into the search queries, the keywords, and on the basis of those keywords, the search queries, they will say whether we have the chance of flu or not, right? So they look for some probably the symptoms like headache, fever, aspirin, right? So all those things that a person with the flu-like symptoms would search for on Google, right? So these keywords they looked at, and they came up with the model which will predict the flu trends. So if you look at this plot, right? If you look at this plot right here, let me change this to the pointer. Okay, so here we are starting. So the red that you have is the prediction by CDC, and the blue prediction is done by Google. So initially Google was kind of slightly higher than CDC, but very soon Google started following CDC very tightly. Alright, that means that Google was very close in terms of prediction as per the CDC. But something happened right here. Okay, at this time you can see that Google is totally off, right? So Google created a kind of a panic saying that we'll have a lot of flu cases, but the reality was a lot lower than that. Okay, now we need to look into this, and we should try to find out like what went wrong. What was the reason behind Google performing so badly when it was already doing so well in terms of their prediction when those are compared to the CDC? Now, there was some very interesting result published as per our textbook by social scientists who looked at it, and they were able to figure out that the reason why Google performed badly was that around this time, Google added this feature of auto correction or auto suggestion, you may say. Okay, so when you type for something, Google will suggest something or some keyword, right? So if you're saying headache or fever, then Google might suggest search for aspirin or something similar to flu. So it so happened that because of this the search suggestion feature that we have here, the search suggestion feature that got added into Google resulted in people being diverted a little bit, right? And they were kind of diverted to the search which was focused towards flu, because of which the number was totally different, far higher than the reality. Okay, so why did that happen? What Google should have done? Well, the Google should have looked into the consensus issue. Google should have verified its results right here. You can see some inconsistency at this period also, right? So from here onwards, you can see that the Google is giving a higher value for the flu kind of outbreak compared to CDC. So it seems to me that at this point they kind of were doing it of their own. They were not looking at the other models, right? The model by CDC, because of the lack of consensus. Okay, so that was the reason why Google failed right here in doing the right prediction. They did not do what was required to do, consensus. Now there's another interesting thing that Nat Silver says. He says that, or he does, Bayesian reasoning. So he says that Bayesian reasoning is very interesting when you have a live model. So what does it mean? So now, because of the very I don't know, but I find Bayes' theorem very simple, and but it is very powerful. It has a lot of application in machine learning. There are a lot of algorithms which are based on Bayesian reasoning or Bayesian concept. So, in similar, philosophy, Nat Silver says that we can make use of Bayesian theorem, and we can use Bayesian theorem to incorporate the new information or the new evidences that we are getting in our modeling. All right, so let's look at this thing. Assume that you know the probability of an event as PA. So PA means the probability that certain event will happen, and that's how you are predicting that event to happen, and it is called prior probability. Alright, so this is prior probability PA, which you know from the data set and which may determine the output of that event A happening. Now what you know is that you have this conditional probability of A happening when a related event B happens. Alright, so if you have this posterior probability of P of A happening given the incidence B happens, then you can make use of these relationships and can improve the probability of A by using this expression. So now you have more information. You will get the improved probability which is conditioned on B. So you can make use of this Bayesian reasoning in improving your result of the model. So now you have probability of event A happening provided B has already happened, and A and B are kind of dependent on each other. to some extent. So you can compute probability of event A happening given B has already happened using the Bayes reasoning. You have the value probability of B given A, and you have probability of A, and you have the prior probability of B as well. Alright, so this posterior probability which you are finding out here, posterior means once this event has happened. It can be computed, which is the refined probability using the available likelihood probability, which is probability of B given A, and the probability of the prior probability of A divided by the prior probability of B. So this is very simple application of Bayes theorem in finding out or refining the probability of the event A condition on B, and it can be used in updating your confidence about the event. Okay, and that will happen when you have your model as live, where you can incorporate more information as and when that is coming. Now there are some other steps also which are very important in building the models. So till now we looked at three philosophies: Occam's razor and bias-variance model, and then we looked at the philosophies of Nat Silver. Okay, now let's look at what are the other things that we should keep in mind. Well, we followed some philosophy. It could be Occam's razor, or it could be the suggestions by Nat Silver, or we used bias variance kind of philosophy. Now the other thing that we have to do is, like, how should we model? So for that we should identify, like, what should be the output for our model. Should it be probabilistic or not? So as it has been established till now that the best approach would be to build a model that will output the probability distribution, right? Giving yes or no, or cancer or non-cancer is not a good output. We should rather have an output like 70% cancer, 30% non-cancer, right? Something like that. And then there's an interesting thing which we will get into now. It is about the baseline model, right? So probably in the next few slides are dedicated to this concept of baseline models. When you are doing a modeling, always have one baseline model. Okay, and then it is sometimes possible to decompose the model that you are building into different submodels. All right, so if you are making a really complex system, like predicting the stock value or stock price of a stock in 1 month from now, then since this stocks behave strangely, and there are a lot of variables that go into it, and that which are important in predicting the stock movement. So you might like to decompose the system into various subsystems. Maybe one system that is looking at the situation of the economy around us, the other model looking at the performance of the company as such, and there can be some other models as well. So the point is, sometimes when your system is really complex, which you are trying to design, it helps if you could decompose decompose your one model into different submodels, and then integrate those models into final task. Okay, so that was about your modeling. If you want to build the model as a hierarchical model or just flat one model, and then when you have to test, right, when you have to evaluate the performance of your model, then the recommended approach to evaluate your model would be to look at out of sample predictions. You should not try to evaluate your system's performance on training data or even test data, because, see, training data has been directly involved in learning, so we should never use training data for predictions. Similarly, testing data should not be used for evaluation. We should have a different data. Ideally, we should not have seen the data at all. But if that is not possible to do, then before building the model, we should separate one data out just for the evaluation process. Okay, so these are some important bullet points for building an effective model. All right, so now there are some philosophies. Okay, so there are a lot of theoretical stuff you'll find in this lecture for the initial part at least. So there are some approaches to modeling, like first principle model and data driven model. So what are first principle models? So I think I looked at this one, may not be more systematically, but now you have the definition of these modeling methodologies, like what is the first principle model, what do we mean by data driven model. So the first principle models that we have are often based on some theoretical explanation, right? So like as I mentioned, if you are working on some data that relates with some phenomena which is explained by physics, like the law of motion, right? So in that kind of a case of cases where we have some insight about the data from the system itself. Okay, like if you the data is generated by simulations, so the simulations are governed by some good understanding of the system. All right, so using that understanding of the system, we generate some data. Okay, that is called simulation. So the first principle models are those which are based on some theoretical explanation of the process. All right, so if someone has done some research, let me give you an example from the author of our textbook, Professor Skinner. So if someone has done some research in the past and the research says that the person who's winning the election depends on the state of economy, right? So this is some theoretical study that the other person has done. So if you're using that model, which is based on some study that establishes that the person who wins the election relates with the economy, then that is first principle model. Okay, because we have a model and we'll use that model to make predictions, right? So our prediction will not be based on data, it will be based on some findings, some theoretical explanation by someone. Okay, and we can have similar situations from science, right? So there are a lot of, like if your data is coming from physics and the data is coming from some well defined principle, right? Then that's the first principle model. Whereas data driven models are different. All right, so here we don't have much of idea about any theory which is generating the data, and what we will be learning from data itself. And for that we will look at different correlations that might exist between the features of the data and the variable that we want to predict. Okay, now the point is, like, what should we do if we have the freedom of using the first principle model as well as the data driven approach? Then what should we do? Well, use both. Okay, so as an example for this election case, so if someone has done some research that relates the person winning the election relates with the present economy, the situation of the present economy, then we can use that uh, model as well in our final prediction. So we can have a model which is a mixture of both. You'll get some data. You'll have a model which is directly based on data driven model. Then you have a model which is based on the first principle model. You can combine the results from these two and you can have a final model. So it is possible to integrate the models also. So the best policy would be to mix these two if you have these available. Alright, so now let's look at the baseline models, right? So I mentioned at least twice in this lecture that baseline models are important. Okay, so uh, the point is, what are the baseline models, right? So the first step to assess whether your model is good is to build a baseline model. Okay, so first step should be to come up with the baseline model, which should be a very which should be a simple but a decent model, which may not require a very sophisticated machine learning algorithm And that's something we should have before we start building our more complex model. And the baseline model should be based on some facts, some reasonable facts, and we will discuss about like how should what could be the candidates of baseline models in the next slide. But that is one of the first step that we should have before we start um, you know making our own model. And why do we need it? Because you may do all the hard work, you might spend months in developing your most sophisticated model that you might feel proud of, but before even getting that sense, you need to compare, right? Like, okay, the first thought that I have in building this kind of a model was very simple, and let's see what's the result I got using that simple baseline model. And then I spent, say, 6 months working on this research, and I ended up with this deep learning based model. Now, how does this deep learning based model compare with my baseline model? Okay, so because of this assessment of the performance in comparison to the baseline model, this is very important, right? So it is recommended to have the baseline model first, so that you can assess your ultimate performance, right? So that's, we already have it here. The first step to assess whether your model is any good is to build a baseline. All right, and then you can always compare your result with the baseline model. All right, so if you're building a classifier, you might start with a very simple classifier like logistic regression. That could be your baseline model, and then you might try some maybe the state of the art deep learning based classifier, and you would like to compare that performance with the simple logistic regression approach. Okay, so only after you decisively beat your baseline model, your model would be considered effective. Okay, so yeah, when you from this comparison of the performance of your deep learning based algorithm, as an example, compared to your baseline model, which I said could be your logistic regression model. Now you looking at this difference in the performance only, uh, you will say that yes, you were able to beat your baseline model. That means you did a good job. Alright, so now the point is like, what should be the baseline model? Because as I was telling you that only if you beat your baseline model will say that you have done a good job. So this was something you should keep in mind. So I'll start bottom up. So I should say that baseline model must be fair. Point is, what do you mean by fair? It should be simple but not stupid. Alright, so this is important. Make sure that your model is simple, not too complicated, but it should be reasonable one, right? It should not be a very stupid model which is doing horribly wrong. Okay, then it won't be considered as a baseline model. So baseline model should have some some substance. Okay, so now let's look at the representative baseline models, like what we can consider as baseline model and what not. So assume that you have to it's a binary classification thing, where like uh, say the problem is whether the stock price will go up or not tomorrow. That's something you have to do today. You have to predict whether the stock price will go up or down tomorrow. So for that thing, we can start with a very simple uh, you know baseline model, which will correspond to simply flipping a coin, right? So that flipping of the coin would become our baseline model, which will say that it will go up with the 50% probability and it will go down with 50% probability. So for this stock kind of a scenario, the uniform random selection, as I'm saying, using a flipping of a coin is good enough. Alright, so it depends on the kind of application that you're working on. For stock prediction, whether it's going up or down, you may use a very simple baseline model which will say yes, it's going up with 50% probability, or no, it's going down with 50% probability. That will be easily simulated by tossing up a coin or flipping the coin. Now in certain cases, right, let's look at the second point. Excuse me. Now this will make more sense when you have uneven data, right? So this first point I'll say for even data, even class distribution, I should say, even class distribution, which means that you have 50% chance of going up, 50% chance of going down. All right. So, but in certain cases, you may not have the data distribution so even. So, as in case of the cancer classification problem, you might have less number of cancer patients compared to the healthy patients, right? So, in that case, you will have uneven class distribution. Okay, so uneven class distribution. Example, 10% cancer, 90% healthy. So in this kind of a scenario, it might be a good idea to have a baseline model which will return the result as the common label. Okay, so your baseline classifier will mostly say, okay, this guy is healthy. All right, this guy is healthy, because that is the more common label. Okay. Now the third one is the interesting one, which is based on single best performing single variable model. What does it mean? Okay, so here it's a very interesting suggestion actually, which is about what could be an interesting baseline model for comparison. So it says that assume that you had 30 variables, right? Okay, just like the example I had. So there are 30 variables in your data set, and ideally you may like to include all the 30 variables in your modeling. Now as a baseline model, what you can do is on the basis of your understanding of the data and also on the basis of some EDA that you do, you might find out those one attribute that highly correlates with the output that you have to predict. Okay, so if that one attribute is highly correlating with the output that you want to predict, then why not create a model just based on that one feature that highly correlates with the output? So that will be the best performing single variable model, all right, which you can use for building your model, and that will be your baseline model. Anyway, for your real model, you will be using more than one feature probably. All right, so that could be a good candidate for your baseline model. Now the fourth point that we have about the baseline model, it relates more with the time series data, right? So if you're building a model that will determine the weather tomorrow, okay, so for that probably you will do a lot of study, you will have a lot of features in your model, and that model will determine what the weather would be tomorrow. But for this kind of a model that you have to build, this very interesting baseline model would be to look at the weather condition today. All right, and on the basis of that you may say, okay, so tomorrow's weather would be the same as today's weather. So if it is raining today, it will rain tomorrow. If it is sunny today, probably it will be sunny tomorrow. So it's a very safe baseline model, which I believe would be very difficult to beat. All right, and then in the last point you may use some heuristic which depends on your understanding of the system. All right, so this was about the baseline models, like why they are important and how we should pick a typical baseline model. Now let's look at the different kind of models that we can build. So there are a number of ways in classifying the kind of models. So we have linear versus non-linear models, we have a black box versus descriptive model, stochastic versus deterministic, flat versus hierarchical, So we will not look at all of these classifications, maybe one or two. So I can give you some idea about linear versus non-linear. So in linear models, you have the examples like linear regression, which are kind of based on the concept of a line, where you try to fit your data in a line and you find out the different coefficients which will determine the weightage of different you know features that you have in the data for the prediction task. Whereas you can have non-linear models which are more complex and are able to fit the data better compared to linear models. All right, so there's these techniques. Then you have general versus ad hoc models. So general models are those models which are not specific to the data. As an example, if you are using some classification or regression techniques like maybe linear regression or logistic regression algorithms, so it does not, I mean, what you can do in most of the cases is that you can change the data, but the algorithm will be the same. The classification algorithm will do the classification irrespective of the data that you feed in. Similarly, the regression algorithm will give you the regression result, but it is not problem specific, right? So it is something which is general enough, right? So which can be applied to a different class of different types of data. So if it is a classification problem, doesn't matter whether your data is from medicine or your data is from sports or your data is from anywhere else. You can use the same classification algorithm for different kinds of data, and these are all general models which have not much to do with the background or with the domain from where the data is coming. Okay, so these are some general algorithms which can work on a wide range of data sets. And we don't have any problem specific idea that goes into their building. All right, whereas the ad hoc models that you have, these are built on the basis of the problem that we are dealing with, which will need domain specific knowledge. All right, so now the problem is that what approach should data scientists be using for solving a problem? Should that person exploit the domain knowledge and come up with a model, or should that person uh, get some standard machine learning algorithm and should apply that for modeling? So the answer to that is that have a combination of these two. All right, your understanding of the domain is important. At the same time, sometimes combining that with the machine learning algorithm also helps. But according to the textbook, I'll say that it will be good idea to use the ad hoc model if you have good understanding of the data. So data scientists generally seek general models, right? General models means machine learning based models, but um, people may prefer ad hoc models over the general models, probably for the reason that this modeling that we are making in ad hoc is based on the domain, and sometimes the domain based models perform a lot better than general models. Okay, so now to the next class of um, the next approach in which we can classify models is black box versus descriptive. So black box models are those models where you get the idea, you get the result, but you don't understand like why did you get that result. So that information is missing in black box based models. You feed in some input and you get the output. You don't get the information like why did this model give you a particular output. Okay, which is not very good, because at times you would like to know like why did your model classified somebody as having cancer versus being healthy. Okay, so there are some models like linear regression, decision trees. These models, they belong to the descriptive model. Linear regression is descriptive model, because once you train your linear regression, then during the training process you'll get the idea about the coefficients, right? And the coefficients mean a lot. The coefficients will tell you like how much this regression has given a weight to a particular feature. Alright, so linear regression is descriptive. It will give you some idea. It will give you the output as the coefficients as well, the value of coefficients, along with the prediction that it is doing. Similarly, the decision tree, we don't have decision tree here. Decision tree is also descriptive model. Whereas there are some other models where you don't get to see what is going on behind the scene, and a perfect example of the black box kind of model is neural network. Alright, so these are generally opaque in the sense you don't know how is the, why is the model giving you a particular output. So an interesting thing has been mentioned in our textbook, which is about an experiment which was done to classify or distinguish the cars from the trucks. So it was based on some images of the cars and the images of the trucks, which was fed, and it was trained. The model was trained to distinguish the car's image from the truck's image. And then after getting a very good performance on the training, this model was tested on tested data, and unfortunately this model did really badly. And I think it was neural network based model, and the reason why this model did badly, which was not explained by the model, was that when the pictures were taken for training, the pictures of the car was taken on a sunny day, whereas the picture of the truck was taken on the cloudy day. So because of that feature, actually what happened, the model learned the background as well. So kind of it associated the sky condition with the object that it was supposed to distinguish. So these are some positives of descriptive models. You will know the explanation, like why is a model giving you a certain output. Alright, so now there's another concept of levels of modeling. So I think I gave you this idea. If not, then let's go have a look at it. Now, interesting and complex models, if you have to build, they will have different levels. Alright, so like this stock prediction example that I have is about stock. So what can happen is some interesting problems which are complex, they will have different levels. Alright, and each of these levels can be modeled as submodel, some independent submodels you can have for the model that you have to build. Alright, example, let's look at the future price of a stock. Right, so when you're saying you have to predict the future price of a stock, then there are a number of things which will determine how the stock will behave. So all these factors which will determine the price of the stock may be modeled as submodel, independent submodels. Example, well, the stock will depend on the general state of the economy. Okay, so we should have one model which will determine what is the state of the economy, and is there something which will determine the state of economy or not. So one model will determine the state of the economy. The second submodel may be based on the general performance of the stock. Right, so if the stock has been doing really great despite the very bad economic situation, then probably this will continue to do better. Alright, so we are looking at different factors that are important and in this modeling task, which is a little complex, and all these submodels which are independent, they can be modeled using submodels. Okay, so what's the third thing? The performance of the industrial sector. Right? So it may depend. See, if just as an example, assuming that as is the situation currently, we are facing the situation of COVID. So a lot of companies, they suffered negatively, but there are some other companies who are doing well. right? Like the companies who are manufacturing the medical equipments, like who are manufacturing ventilators and all, they are doing good for the reason that there is a demand for that. Okay, so it might make sense to have a model which will model the industrial sector as well. So if in the scenario of a pandemic, your company whose share price you want to check happens to be in the healthcare industry, then probably this company is going to do well. All right, similarly we can reason about e-commerce companies as well. All right, so the message is that if your system is complex and it is possible to have levels in our modeling, then we will think of splitting that into submodels and then modeling each submodel independently and then combining the result into the final model. Okay, so that's the same thing. Okay, so this is in continuation with what I mentioned, but it has to do with the kind of models that you have. Unfortunately, this hierarchical decomposition will not be possible in case of a black box kind of a model, right? Because we don't know what is going inside that. You have some input and you get something as an output. All right, but if you have the situation like the stock prediction, right? And luckily, if you can model that into different levels, then for each level, it might be possible for some levels, right? For some sub problems, not all, for some sub problems, you may be lucky to find some theory based first principle model. All right, so if you have some theory that governs the general state of the economy, like the point number A, then for that sub problem you may very well use the first principle model. Okay, first principle models are those which are based on some theoretical foundations. All right, so this will be handy, and you can maybe use some other models using data driven general model. To the evaluation part, it's a very important thing. Once you have designed your model, you would like to check how well your model is performing. So here, let's start with the classifiers. So your model can can be categorized into either the classifier or could be a regression kind of a model. So let's understand the evaluation part from the classifier's point of view. And we are considering a simple case where you have binary classifier, which means that it will either classify the output as the positive or negative. So before that, we should have some understanding of what is positive and what is negative. So this is a binary classifier, and the classifier can give some output as whether the sample belongs to a class or it does not. So there is a notion like what is positive and what is negative. So usually there are certain rules that which class should be called as positive and which class should be called as negative. So for that this example, let me consider a case which is about the cancer. All right, so our data is about cancer, and we need to predict whether a specific sample corresponds to cancer or not. So in this case of cancer, where we will have probably imbalanced class distribution, so this data would be probably imbalanced, and that means you will have a more healthy data, more healthy sample, and you'll have less cancer sample. So in this kind of a situation where you have one class which is less in number and the other class is more in number, like the cancer is less in number, so the label that corresponds to cancer would be called positive, and the other class which is non-cancerous would be considered as negative. So let's discuss this concept of classifier evaluation from this example in point of view. So you have designed a classifier which has learned on the data, and you want to classify the patients as having cancer or as being healthy. So let's see how will we evaluate the performance of this classifier. So what can happen, right? Let's look at these four scenarios. You're given a sample, and you will pass on that sample to your classifier, and classifier may say that this sample is positive. Positive means that this guy has cancer, or you may say that this is negative, meaning that this person does not have cancer. So now there are some possibilities associated with this prediction. So what do we mean by true positive? Let's try to understand what is true positive. True positive means that, fact means the reality, right? Or you can say observation would be something which is true. So observation is that the person is positive, that data corresponds to a cancer case. That's the observation. And your prediction is also positive. So the reality, which is the fact that the data which we are testing using our classification corresponds to a positive cancer case, and the result that we are getting after applying the classifier is also positive. So that we'll call as true positive. Positive was the reality, and positive is the result of our classifier. This is true positive. We can have a different scenario where the sample that we have corresponds to, in reality it corresponds to a negative case. That means we are feeding an example to test our classifier that corresponds to a negative case, a person being healthy, and our classifier is also saying that the person is healthy. Okay, so classifier is truly identifying a negative case, that is called true negative. Reality is negative, and our classifier is also saying negative. So true positive and true negatives are good results, and these are the results in favor of the classifier. It says that the classifier is doing good job. It's classifying positive cases as positive. So the number of positive cases that the classifier classified as positive will count for true positive. For true negative, these are those examples which were negative in reality, and the classifier also marked those classes as negative. So true negative, true positive. Now what is false positive? Okay, so false positive corresponds to that class or the sample which was in reality a negative sample, but because of some mistake the classifier classified that to positive. So the classifier is saying it positive. That means the classifier is saying that this guy has cancer, but in reality it was negative. So the claim by the classifier that this sample is positive is false. Okay, so that's what we mean by false positive. Similarly, what is false negative? False negative means that the reality was that the sample corresponds to a cancer patient, but the classifier that we have is calling that as the healthy patient, right? So you are saying that the sample is negative, you are saying that the sample corresponds to a healthy person, but that is false. Okay, so these two things that you have, which is false positive and false negative, are the numbers which will go against the performance of the classifier. Okay, so we want higher true positive, we want higher true negatives, but we want lower false positive, and we want lower false negative. Alright, so all these four parameters that you have, which we can compute on the basis of the performance of the classifier on the tested data, can be tabulated right here. So what you're looking at here is called the confusion matrix. Confusion matrix. So why is this called confusion matrix, and what do we have here? Well, if you look at this column here, so then this is about the predicted. That means it will have the result of our experiment on the classifier. What is the classifier calling, right? Whereas right here it's the actual thing, right? So this is the reality in the test data. In the reality, we had some positive cases and we had some negative cases. All right, so this is the reality. All right, so we had some positive cases and some negative cases in reality. And what did we predict? So here we have predicted. So that means out of those positive cases, true positive corresponds to those numbers which the classifier predicted as positive and are in fact positive. That's the reason we have it as green. What is true negative? True negative means those the number of samples which were predicted as negative and were in actual negative as well. Alright, so that's the reason this is in green, which is a positive thing about our classifier. Classifier is finding negative cases as negatives, correctly identifying negative cases. Classifier is correctly identifying true cases. Okay, so true positive, true negative. What is false positive? Well, look at the actual actual information. In actual or in reality, these samples were negative, but what happened? By mistake, the classifier is predicting them as positive, right? So by mistake its prediction is positive, but in actual these are negative. So this is false positive. And we can have the same reasoning for false negative. Look at this column. In this column corresponds to the actual case, and this cell that you have is actually positive, but because of some issues with our classifier is marking those as negative. So this is false negative. Alright, so this is an important concept about the evaluations. So once you have these values which you can get from the experiment that you're performing on the test data, after training your classifier, then you can form some measures, performance measures on the basis of this matrix that you have. So you will replace these cells with the numbers that you get after conducting your after checking the performance of your classifier on the test data. Okay, so here we have there's another interesting thing about the classifier. So it relates to the same example as I have in the previous slide. We have some patients, um, patients with cancer on the right hand side and patients without cancer on the left hand side. And let's think of this boundary which depends on some threshold, and using that threshold we are dividing. I mean, there is a rule actually. So this threshold is a rule which will determine that if this, let me call this x-axis, all right, so you have the value on x-axis which will determine whether the patient is positive or whether the patient has cancer or not. So using this diagram I can have this rule which says that if x is greater than or equal to 0.5, it is cancer. Alright, so that's something you can see from this figure as well. This is the threshold. The vertical line that you see is threshold. Okay, let me erase that, it's not very clear. Erase. Threshold. Threshold means a value which a classifier is using to determine whether that sample corresponds to the cancer case or non-cancer case. And x is some score that we are getting from the classifier. So classifier is giving us some score. You can interpret that as a probability as well. Okay, so if the probability is greater than or equal to 0.5, we'll call that as cancer. And this is the probability of patient being called a cancerous patient. Alright, so here if you want to understand this table, the confusion matrix from the reality in terms of the distribution, then you can use this as well. So here these things that you see, right, all this is true positive. Okay, in fact this whole thing that you see in the red, if you forget about the green, okay, no, this thing is true positive. All right, all this region is true positive. That means look at the red curve. These are all true positive cases. Why? Because those were positive and your classifier is correctly classifying those as positive, right? So there is this overlap which might be resulting in some confusion, but just pay attention to the red curve and the portion of the red curve which is on the right hand side of this threshold. All this is true positive. Okay, why true positive? Because these were positives and the classifier is classifying those as true positive. How about this region which is positive, but because of the threshold it is being declared as negative, right? This is the threshold. So this portion that you look here, which is red curve, but on the left hand side of the threshold, it is false negative. Why false negative? Because these were actually the cancer patients, but because of this threshold and because of this issue with the classifier, this section is being marked as negative. So this is false negative. Okay, and similarly, if you look at the portion of the green curve which is on the right hand side of the threshold, let me highlight that, then this section is being incorrectly classified as positive. So this is false positive. Why is this being classified as positive? Because of our threshold. Our threshold is such that if we are using this threshold and the rule right here, then even these patients which are in fact not cancerous are being classified as positive. Okay, and this portion that you have, all right, of all the green curve, and let me make that in this way, all the green curve which is on the left hand side of this boundary are true negative. Why true negative? Because these are negative, these are green, these are true negative, because these are in actual negative and are also being classified as negative by this threshold. Alright, so this is another way of looking at this confusion matrix, but right here we are looking at the distribution and threshold. Okay, good. Let's move on. Now we have some measures, right? Some metrics or statistics which will help us in evaluating the performance of our classifier. So the simplest one is accuracy. So how is this accuracy being formulated? Look at the true positive thing, which means the cases which are in actual positive for cancer, and these are being marked as positive by the classifier. Okay, so this is a factor which is in favor of our classifier. True positive, positive cases predicted as positive. True negative is again a positive news where the classes were negative. I mean the data sample in reality is for non-cancerous patient and our classifier is saying so. Alright, so true positive plus true negative means doing the correct prediction, divided by true positive plus false positive plus true negative plus false negative. Okay, so here we have all these numbers that we have, so this will be if you add these things up, then this number will be equal to the number of samples that we had in the test data. Whereas true positive means the number of samples which were correctly classified as positives by our classifier. True negatives are those samples in our test data which was correctly classified as negative by our classifier. Okay, so now this accuracy number that you have, it will be in the range from 0 to 100. 100% actually, if you are thinking of percent. 0 to 100%. Now when will we have 0%? When you messed up altogether, right? We did not get any true positive, we did not get any true negative, which would be a rare case. But if you want to think about the scenario like when will I have the accuracy as 0, that means none of the positive samples were correctly classified as positive, and similarly none of the negative samples were correctly classified as negative by the classifier. And when will we have this 100%? Well, that will happen in the case when you were lucky and all the positive samples were correctly classified as true, as positive, and similarly all the negative samples were correctly classified as negative. In that case, the false positive would be 0, and similarly false negative would be 0, and it will be 100%. Okay, so now this is an interesting discussion actually in the textbook, where where the textbook says that we have a monkey who's doing this thing, right? So in place of any intelligent classification model, if we think of some approach which is kind of a monkey approach, where it will randomly pick the sample and randomly mark the sample as positive or negative, right? If that is the case, with the 50% probability of marking any sample as positive and 50% as negative, the resulting accuracy would be 50%. Please work on it, right? It should not be difficult. Okay, so there are some issues involved with the accuracy, and accuracy has a problem. Alright, so let me tell you about a case where the accuracy may have a problem. So for that reason, I will erase these things that I have here to reduce the clutter, and let me show you some issues with the accuracy measure. It will give you some idea about the cases where accuracy is not a good measure to evaluate the performance of a classifier. Now let's think about a scenario where we have number of samples is equal to 100. Okay, and in this case the positive sample, which is cancer samples are let's say only 5. Alright, and negative samples, which is a healthy one, is 95. Alright, so this can happen. It can happen in the case of cancer kind of a sample, where it is very rare to find the data sample for one class, which is the positive class, like cancer. So let's try to put this thing in here and try to identify like what would be the accuracy for one classifier. And let me give you an interesting classifier, because our purpose here is to see is to evaluate accuracy as a measure, and my claim is that accuracy is not a good measure in certain cases. Alright, so my classifier that I have, has a rule that the rule is very simple, and it says that all the samples are negative. Okay, so we are evaluating the performance on these 100 samples, and of those 100 samples, the positive are 5 and negative are 95. Alright, so let's see what will happen. The classifier is very simple, which is saying that everyone is healthy. So what will happen here? True positive, right? So did the classifier say that anybody has cancer? No. True positive is 0. Why? Because the classifier is saying, everybody is healthy, no positive sample. So true positive is 0. How about true negative? There are 95 negative cases, and this guy is saying 100 are negative. So out of those 100, 95 have been correctly identified as the cancer patients. So 95 is right here. Okay, and then true positive is 0. False positive is 0. This guy is saying that no one is positive, so no false positive, nothing as true positive. And then true negative is 5, right? Incorrectly, this guy is saying that the positive cases are also negative. So these 5 people who are positive in the tested data, the classifier is saying that no, these are negative. So that 5 is false negative. False negative is 5. True negative is 95. Alright, so what is the accuracy? Accuracy is 95%. Alright, so 95% means a very good result, right? But what is this classifier doing? Classifier is doing nothing at all. Okay, maybe this classifier is useless for us. Our task is to is to identify a person who has cancer, right? But accuracy is a horrible measure for that, because you can have this extreme classifier that is calling everybody as negative, and negative samples are more in number, very extremely large compared to positive samples. So you might end up with a very good accuracy, 95%, which is just useless. Okay, so this is misleading. Accuracy is a misleading measure for for evaluating a classifier's performance when your classes are skewly distributed. That means one class has more samples compared to the other class. So because of this, we need another measure, which is precision measure. So let's look at the precision measure. Like, what do we have in precision? So the same point, when p is very less than n, p was 5 and n was 95 in our example, accuracy is a silly measure. We just established that. Now if only 5% of the test says cancer, are we happy with a 50% accurate monkey? Alright, so that's a different thing altogether. Let's look at this precision measure first of all. Like, what is this precision? So precision is formulated like this: the true positive that you have divided by true positive plus false positive, which means that out of those samples that you're marking as positive, how many of those are really positive? Okay, what is false positive? You are wrongly claiming some samples to be positive. What is true positive? You are correctly identifying some cases as positive. So if we put this formula in the previous case, then what value are we getting? Our true positive is 0, right? Then a false positive, true positive is 0. So this will have a 0%, 0 precision. Actually here it's coming out to be 0 by 0, which is 0 plus false positive. Okay, you don't have any false positive here. So this is an extreme case. Actually we will have to change this a little bit, right? So this thing should be changed a little bit so that we don't get 0 by 0. Assume that we have 1, right? I'll change this example a little bit so that we don't have 0 by 0, assuming that okay, so assume that, let's change this example a little bit to have the false positive thing as 1 to avoid 0 by 0 thing. So what will happen here? You'll get a 0% precision, which means yes, your classifier is really bad. because the classifier is not even able to find out one positive case. This is a modification I did, right? False positive, I made it 1, otherwise it was 0 by 0. I hope you follow that. Alright, so this is a better measure compared to accuracy. It will truly identify the performance of a classifier. Okay. Alright, so we have one more measure which is called recall. And how do we define recall? So recall is defined as the number of true positive divided by true positive plus false negative. And how should we understand this? Well, this will evaluate like for the portion of the true positive cases that you were able to identify. Right, so what is false negative? So false negative means these were true classes, these were true, but you got it as false. Alright, so recall kind of evaluates like how many of the fraction of positive cases that your classifier is able to obtain. Okay, so this is also an interesting measure, but there is a case where even this can give you a misleading result. As an example, let's use the same example where we have 5% cancer and 95% healthy. Right, and let's think about a different kind of the classifier. I'll call this classifier model number 2. And what this classifier number 2 is saying, this classifier number 2 will say everyone has cancer. Okay, so if you're saying everybody has a cancer, then what will happen? True positive, right? These 5% people who have cancer, you are saying they have cancer because you're calling everybody having cancer. So true positive is 5. True positive is 5. False positive is 0 because you're not calling anybody having being negative. So you're not saying anything as negative, right? So forget about having anything for false negative. Alright, so this is 100%, which is misleading again. Alright, so this is silly as well. So you should see that we should be very, very careful about which measure to use for evaluating a classifier. Accuracy was bad, we just saw that. In this case, if you do accuracy, and then you will have some misleading result, as we saw in the first example. Similarly, in recall you have seen it. Now we can do this exercise, right? For the same data, we should find out the precision. Okay, recall is something we found out here. Let's see what would be the precision in this case. So our true positive would be 5. Why? Your classifier is saying that everybody has cancer. So in that attempt, when you say everybody has cancer, you will by accident correctly classify these 5 people as cancerous. These are true positive. So this is true positive divided by true positive plus false positive. Okay, so what is true positive here? It is 5. And what are false positive? This 95. Alright, because these are correctly being called as positive, but the remaining 95 you're calling as positive, which is incorrect. This is false positive, right? This is false positive. So what is the precision that we are getting here? Precision is 5 by 100, which is 5%. So in this case, you can see that precision is doing better. Alright, so the takeaway message is, the message is that often one performance measure is not sufficient. You may have to evaluate your classifier on all these performance measures. If the class is evenly distributed, accuracy is good. But along with the accuracy, it's great if you compute precision and recall as well. Alright, and often it depends on the kind of problem that you're solving. In certain domains, recall is more important. In other domains, precision is more important. You need to think about the kind of problem that you're solving. Do you want higher recall or do you want a higher precision? Alright, so recall measure being right on positive instances. Saying everything has cancer gives a perfect recall. We established that, right? 100% we got that when we are saying that everyone has cancer. Okay, now a good news is that we have a score or a measure which is based on the precision and recall. So this in fact is a harmonic mean of precision and recall, alright, which is more tight. So for that reason, very often people they report their F score rather than reporting the recall or the precision. So now how should we compute F score? This is something we have to learn. So F score is simply 2 times precision multiplied by recall divided by precision plus recall. Okay, so this is more practical measure, more for the reason that it has both the factors in. It has the precision as well as recall integrated in the F measure. 2 times precision multiplied by recall divided by precision plus recall. Okay, so now what is the takeaway lessons for us? Accuracy is misleading when the class sizes are substantially different. Okay, the first example, high precision is very hard to achieve in unbalanced class size. All right, and F score does the best job of any single statistics if you have to use. Alright, but as I said, it's always better to have all 4 of those reported in your result, and all 4 together will give a good idea about the performance of the classifier. Alright, now this is even more interesting thing which is called ROC, receiver operator curves. So in order to understand what ROC is, let's pay attention to what we have in the figure right here. So this figure is about the classification of people into the gender. Okay, so these 2 curves are related, gender and height. So that's the kind of thing we are looking at. So assume that the positive case means, let me write that positive here is male. You can change that, but for this example we are considering positive as male and negative as female. Okay, and how are we determining whether a sample is male or female? It's only on the basis of the height. Okay, so on the x-axis if you consider we have height. Alright, and now the model that we have is deciding whether a person is male or female on the basis of height, and the rule is somewhere here. Okay, so we will have to approximate, I would say probably 167. So our threshold is 167. If the height is more than 167, we will consider that person as male. That's the true positive. Okay, and if the height is less than 167, then we will consider that as female. Or it's true negative, and then this is the true positive. And what you're looking at as the pink histogram and blue histogram are in reality the distribution of the height of male and female. Okay, so that's the distribution, and you have a threshold here. Threshold. Why is this threshold important? Because our rule is dependent on threshold, right? So rule is something like this. You know, you are male or positive if your height is greater than threshold. Alright, so threshold right here is 167. And if you move this thing to right or left, then that will give you a different kind of a result. So the result of this classifier, which we have we have right here, um, will change if you move this threshold. Okay, if you move this value of the height that you're considering as the one that will determine being male or female. Okay, if you move it to the left hand side, you'll have a different result. If you move it to the right hand side, you'll have a different result. Alright, so now let's try to understand like what is the purpose of ROC. What is this curve showing you? Alright, so ROC curve gives us some idea about the performance of a classifier. This curve that you're looking at, which is blue in color with a lot of dots right here, this curve is describing the performance of the classifier that you have here. Alright, and what is this classifier here? The classifier is distributing these two and kind of coming up with a decision like what would be called as positive and which sample would be called as negative. Okay, so it is up to us. When we move it on the right hand side, the classifier will give a different result, because in that case, if you move threshold to the right hand side, then you'll have less true positive, and whereas if you move to the left hand side, you'll have false negatives. Okay, so I hope you understand true negative here and true positive, false negative and false positive, because this is similar to this figure right here. Okay, but this figure is about the different example, which was about cancer, whereas the figure right here in our discussion on ROC is based on height. On the basis of the height, we want to classify people as male or female. Alright, so in order to understand how this how do we get to the ROC curve, we need to understand what do we have in y-axis and what do we have on x-axis. So y-axis has true positive rate. This true positive rate is defined as number of true positives divided by number of total positive. Alright, so what does it mean? Well, let me use this threshold to give you some idea about true positive rate of this classifier. Classifier means when you are using the threshold with the value of 167. So true positive rate means all these pixels that you have on the right hand side of this threshold, which are positive, and your classifier is correctly classifying those as positive. So in case, let me think about this case, for this threshold, if I say that, alright, let's do it, right? Now let's make it concrete. If I say that number of males in our example is equal to 100 and number of females 100 as well, okay, and let's say that true positive with this threshold, right? In this case, these numbers that I have corresponds to the threshold right here, and let me say that the true positive is equal to, for this threshold, is equal to 75. Alright, that means 75 males have been correctly classified as males in this case. So what is my true positive rate? My true positive rate would be 75 divided by 100. True positive 75, correctly 75 males were classified as males, and total number of males or total positives that I have is 100. That is true positive rate. Now what is false positive rate? What do I have in my x-axis? So it will be number of false positive divided by number of negatives. Alright, number of false positive, that means this thing, divided by total number of negatives, which means that how many females I am considering as males in this case, and how many divided by total number of females that I have. To make it simple, let me say that in this case false positive is 25. Alright, so by mistake, out of 100 females that I had, I am classifying 25 of those as males. So my false positive rate would be this 25 divided by 100. Alright, so for this threshold value, which we have, this threshold is equal to 167, I have the false positive rate, which is my x as 0.25 and y is 0.75. Alright, so you might find some point 0.25, 0.25 and 0.75. It should be somewhere here. Okay, or maybe less than that, 0.75, somewhere here. It may not be perfectly coming on this figure, but this is how you compute these values. For different thresholds that you have, you will find different pair of the false positive rate and the true positive rate. Alright, so for when your threshold was 167, you will get this value. Now when you move this threshold right here, okay, so let me have the second threshold, which is around 180. Assuming that this is coming out to 180. Okay, threshold 167, we had this value, but when I move it to the right, if I change this threshold here, move it to the right, then what will happen? Let me write this threshold is equal to 180. Now when your threshold is 180, then what will happen? All these values that you have will change. This will be the same because I am not changing number of males, I am not changing number of females. But what will happen here? Well, now let's do the true positive rate, right? So true positive rate in the second case would be, this was the first, let me do the second case. It will be, assuming that these are only 50 with this threshold, if I have true positive rate as 50, then it will be 50 divided by 100. So true positive rate will fall down to 0.5. Why? Because you moved the threshold to the right. Now you will have less number of samples being correctly classified as male or positive. Alright, good. So what will happen to my false negative rate, false positive rate, right? So my false positive rate is very, very low here. It is up to you what you want to consider. Probably I may say that these are some 5 samples, right? So false positive rate would be 5 by 100. Okay, so what's the value now? Now for the second threshold I have, it will be 0.05. If these are only 5 samples on the right, which are false positive, which were by mistake classified as male. And what's the corresponding true positive rate is 0.5. Alright, so you will find somewhere right here, okay, some value right here. Okay, so this is how we create the ROC curve. Move the threshold. If you move the threshold, then these different points that you have are the values corresponding to different thresholds. And for threshold, you will get the corresponding x and y axis. X axis will have false positive rate, y axis will have true positive rate. And what is true positive rate? It is the number of true positives divided by total positive samples that we have in our example. And false positive is number of false positive that our classifier is giving divided by number of negative examples that we have. Okay, good. Now you might find this thing a little difficult to follow, but believe me, it is not. Let me know if you have questions on this. This is a very important concept in evaluating the performance of a classifier. Okay, so how can we say that the classifier A is better than classifier B or not? So well, we can judge that, we can give some information about the performance of classifier A versus the performance of classifier B by looking at the ROC curve. So what I will do, let me remove some clutter. Okay, and I'll call this as classifier A. Classifier A has this ROC. Now assume that I have another classifier. Alright, so other classifier has an ROC curve like this. This is another classifier with an ROC which is higher than A. I will call that classifier B. And there is a classifier C. Alright, and we need to compare the performance of B, A and C. Then we will say that B is the best. Why? Because this is kind of covering this whole area. Alright, so the higher is your ROC curve, the better is your classifier. Alright, so B is better than A and A is better than C. Alright, so if your classifier is performing close to the diagonal in the ROC curve, then that means your classifier is just like a monkey who is who's randomly generating some labels for you. Okay, so that's the reason why ROC is important in evaluating the performance of different classifiers. True positive rate, false positive rate. False positive rate on the x-axis, true positive rate on the y-axis. Alright, change the thresholds, and for different thresholds you'll get the points on the ROC curve. Now there is another thing actually which is related with ROC curve, that is called area under curve, AUC. Area under curve. Okay, so what is the area under curve for the classifier A that we have on the left hand side? All the area that you get. Okay, if you consider this area, then that will be defined as the area under the curve for the classifier A. Okay, the higher is this area, the better is your classifier, right? So we sometimes even compute the area under the curve to evaluate how good our classifier is. And for the outer classifier, the classifier number B, you have even higher area under the curve, right? So if you shade this region also, then you'll get the area under the curve for the classifier B, which is higher than A, more close to A, more close to 1. Okay, 1 here, 1 here. Alright, so area under the curve is also an important evaluation measure for checking the performance of the classifier or comparing the performance of the classifiers. Alright, so now let's move on to the more complicated case where you have multiple classes. So till now these measures that you saw were for binary classifiers where your output could be true or false. Not true or false, sorry, it's positive or negative. Alright, so just two cases: positive cancer case, negative cancer case. Positive means the patient had cancer, and negative means the patient is healthy. Now how about the case when you have multiple classes? Alright, so for that I'll give you this example, and it's based on some results of the classifier which was for optical character recognition, OCR. So here we have different digits, and these digits are being classified. So probably these are handwritten, and our OCR that we have will read these digits and will try to classify, right? So what do we have here? This is a confusion matrix, just like the way you had for a binary case, but it is bigger because we don't have just two classes, we have 10 classes here. The digits the digit could be 0, 1, 2, 3, 4 till 9, and for each reality, like when somebody was had written 0, now our classifier will we will evaluate the classifier as when the reality was 0, then in how many times the classifier identified that as 0. So here you have actual and and here you have predicted. So how do we read this confusion matrix? Well, uh, in the samples 351 times the OCR was able to identify 0 as 0. Okay, so this is the correct classification. The diagonal that you have here, the principal diagonal, has the correct result or the correct classification. 351 times 351 times 0 was correctly classified as 0. In 254 instances, 1 was classified as 1. 166 times 2 was classified as 2. And 142 times 3 was classified as 3. So this way you can evaluate the performance of your classifier. Like in how many instances our OCR is correctly classifying a digit to the uh, is recognizing the digit correctly. Now here it can give you some very interesting insight. Like pay attention to this kind of higher number, which is 11. What does it mean? This means that when your digit was actually 5, 11 instances, in 11 instances it was incorrectly predicted as 3. Okay, so that is a problem here. 11 instances our classifier did not go the correct way. It kind of messed up in 11 results, and instead of calling predicting 5 as 5, it predicted 3. That's a problem, right? So all these numbers that you have in your confusion matrix are useful. Okay, they will give you some idea about the errors that your classifier is committing, and these values can be used to finally derive the precision value and the recall value, but I did not include that because that might make it more complicated for you to follow. Alright, so now till now we were looking at the classification problems where the output that you have could be a discrete value, or like cancer, non-cancer, and in the OCR we looked at different digits. Whatever the OCR is reading could be one of those 10 digits, 0 to 9. Now let's look at some other kind of models like regression models, where instead of the discrete value it will give you a continuous value, something like the price of the house that you might like to predict in Long Island, right? So when you're predicting a price, then the price could be anything. It's a continuous value. All right, we don't have some fixed set that the price should be only say 500,000, only 300,000. No, it could be a real value. So for those kind of problems we use regression. So if we have to compute the statistics for evaluating the performance of a model which is giving us some numerical value, then how do we use it, right? So for that thing, if we say that the forecast is f, if f is the result that our model is giving and o is the observation, then how do we compute the error? How much we were off from the actual value? So you have the absolute error thing where you find out this difference between the forecasted value f and the observed value, right? So this could be one statistic that you might like to compute for every output that your model is generating. Now this may have a problem because we are not considering the unit. Okay, so make it more useful. What you might like to do would be to do something like relative error, which means let's find out the relative error, which will be whatever has been forecasted minus the actual observed thing divided by the observed thing. Okay, so this will give you a fraction of the error, and this fraction of the error is better than the absolute error because this is unit free. All right, so it doesn't it won't we should not think too much about units now when you have divided the error by the actual value. So relative error is better than the absolute error. Now these two measures that you are looking at are on one sample. right? What was predicted, what is actual. So you got the error on just one sample. If you want to come up with a statistics which will kind of describe your performance over whole test sample, then we have to aggregate these errors, right? So how do we aggregate? You can compute the mean or median of squared errors. So what is the squared error here? So let's generalize it. We have f and o. So what I can do, let me call f as y hat. So y hat means what did I predict, right? So predicted output is y hat. O is simply y. All right, so this whole thing that you have, the difference between f and o, you can write as y hat minus y sub of I. All right, that means your error that you see on the ith sample, what we predicted and what is the reality. Let's find this difference and square that and compute the mean of that. This is called mean squared error. So what is it? Just find the square of the error and let's compute the mean over all the samples that we have in the test data. It's called MSE, mean squared error. That's a very common statistics for evaluating the performance of regression model. Now we have something close to MSE, that is called root mean squared error. Mean squared error you have, now root of that, right? So what does that mean? Whatever you have in MSE, take the square root of that. All right, so this whole expression that you have, we can write that like this as well. All right, where we are using theta predicted minus theta, which is I believe the vector notation for this individual difference that you find out. So in place of this, you can use the notation like expectation of theta predicted minus theta square root of that. This I believe is a vector notation, but it means the same thing. You can use the same expression for RMSD, but then you should not be using theta. You can write it this way also. This is equal to 1 by n summation of I is equal to 1 to n. Then you have yi hat minus yi squared. This is your RMSD, root mean squared error. Okay, so now this is another interesting thing actually, which is about how you should evaluate your model in the best way. So whenever the data is given to us, then we try to split the data in different parts. So the rule is that you should keep 60% of the data for training. The remaining 20% you should keep for testing, and final 20% you should be keeping for evaluation. And you should not touch the evaluation data at all while building the model. Alright, that is the case when you don't have the data. Right, so when you don't have the data and you have to use whatever data is available to you for building the model and also evaluating. So in that case, you should keep 20% of your data for evaluation, remaining 20% for testing, and the 60% for training. That's the rule. Okay, now well, in ideal situation, what you should do, in ideal situation, you should test your model on the data that you have not seen yet. As an example, if somebody is making a model which will predict the performance of, which will predict the result of, who wins the election, right? So probably that person should wait for the final result and evaluate the performance of her or his model compared to the output that we see of the election. Or in other cases, maybe in other simpler cases, what one should do is build the model on the basis of whatever data is available, divide the available data into training and testing, and then once that fellow is satisfied with the model, then that person should be waiting for fresh data to come and as and when they get the fresh data which is not there at all in your training and testing, then it should test the data on the fresh data that he or she has not seen at all. So that is what we have. The best way to assess a model involves out of sample predictions, right? The sample that you haven't seen yet and the sample that you might get in future, and it will be the best, the evaluation data, the best data to evaluate your algorithm. You will be checking on the data that you have never seen, or even better, that data did not exist, right? So that way you'll be doing the best if you could show the performance of your algorithm or the evaluation of your algorithm on unseen data. But if for some reason that you can't do it, you have to finish everything in few days, and then whatever data you have, you need to split that into three parts. Training, use that to build your model. Testing, to see how well your data is doing, and evaluation is something which you will use to finally show the performance. All right, so now this, I believe, is the last slide in this kind of little lengthy lecture. It is cross-validation. Cross-validation is a very popular approach in validating the model, and this is done mostly when we are limited by the data, when we don't have enough of data. Then what do? We divide the data in k data samples. Okay, so if you had as an example 100 data samples, and what we are doing, assume that k is equal to 10. So you will divide the whole data into 10 partitions, and out of these 10 partitions you will use 9 by 10th of 100, all right, for training, right? So what you'll do, you'll leave one sample, one partition out for testing, and you'll use 9 by 10 of the 100 for training, and you'll use the remaining 10 samples for testing. All right, and you will have to repeat it. You'll have to repeat it in such a way that let me make a picture right here. You have k is equal to 10. So let's do 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9 and 10. These are all 10. So what you will be doing, you will leave this one, you will train on these remaining 90 samples, and you will use this for testing. Later on, what you will do, you will include this one also for training and use the second one for testing. Right, so what you are doing in this rotation, you are learning your model on 9/10 of the data and testing it on the remaining one. Okay, so this is, and finally you will evaluate, or you will report the result as the average of your performance. So when we do not have enough of data to separate training and evaluation data, what we do, we train on k minus 1 by kth of the data and evaluate on the rest, right? So 9/10 of the data you will train, and then you will evaluate on the remaining 1/10, which is 10. Then keep doing it, right? In every iteration you should be changing this 1 by kth sample for testing. Alright, so with that you will finally do an average of the performance, and that's what you will report. Okay, so that was it. Alright, and I'll see you in the next lecture. Bye bye.